Everything you wanted to know about Plasma, but were too afraid to ask. And now, to talk about Plasma, including scaling and payments, please welcome Plasma researcher Georgios Konstantopoulos.
Okay, perfect. Hi, everyone. Thank you for coming. It's been a long day. So I'm going to talk to you about scaling, Ethereum, other chains. So you can find my slides at this URL if you're interested in following along. So I will not motivate this too much. There's a clear chicken egg problem. Do we get the users and scale afterwards? Or do we scale and we say that our chain does 100 TX per second and we get everybody? You will need to solve scaling at some point. So moving forward. There is two approaches to scaling, on the base layer and on layer 2, what we say. So on layer 1, what you will see many times is that the sharding technique that's being used for Ethereum, other consensus algorithms, improving the virtual machines, and other techniques. And on layer 2, you have Plasma, which is a similar concept to sidechains, and payment channels and state channels, which are at a very good stage right now. And to get this out of the table because I want to clear a small misconception that at least I believe, sidechains are not a scalability solution per se. So what happens in a sidechain is that you have the sending chain and the target chain, where usually the target chain is one that's much faster, which is able to give you the scalability that you want to do. And what happens is that I lock one Bitcoin on BTC, on the BTC chain, and then somehow one BTC appears on the, let's say, the liquid sidechain. And when I want to get my money out, after I did my 10,000 transactions per second, I go back to Bitcoin, I say unlock my funds with these are the proofs. But if your chain is more secure, more scalable, I will claim that there is some inherent trade-off towards its security. And so what happens is that maybe the sidechain, it censors your withdrawal transaction. It doesn't allow you to get your money out. What are you going to do? You lost your money. This is a problem. So the claim is that the sidechain is primarily an interoperability solution. It's not a scalability solution because the moment your funds leave the starting chain and they go to the destination chain, the security of the funds changes. When it was in Bitcoin, it had some exahashes per second security. In the liquid sidechain, it has the security of 4 multisig, signatories or whatever it is right now. So it's better to think of it as layer 1 that speaks to other layer 1s. And if each chain is independently secure, that's perfectly fine. On layer 2 now. So layer 2 is this technique which allows you to basically do more scalable things while maintaining security. And I keep saying the word scalability, so we'll appeal to the authority here by Jameson Lopp, a very good developer, who says very accurately that scale is how much we process. Scalability is how much we can keep scaling while keeping the cost low. And this is what we want to do, because EOS scales, but it doesn't have good scalability. So what layer 2 does is that we maintain our high performance, we inherit the security from layer 1, but while keeping the cost at layer 1 low. And by saying that we inherit the security of layer 1, if you're using an insecure layer 1, you still have a problem. So I would usually say that you want to have some proof of work chain or some very high stake based chain. How will we do that? How does that happen usually? What is the anatomy of a layer 2 solution? Usually, it has 2 components. It has a smart contract, where in the smart contract, you take some funds, you lock them in the smart contract, and then something happens. And that something that happens is that your funds are available in the layer 2, which is either they're now available in the sidechain, or they're in a payment channel, or whatever. Then you start transacting, so you make your transactions, you scale, you're good. And then, when you want to withdraw your funds back, you need to make a settlement request. So you try to play a game where you wait some time until you get your funds out. And usually how this looks, which I will call the deferred settlement game, taking the term deferred from Nick Carter's article. What happens is that I start the settlement, I say, please unlock my funds, these are the proofs. I wait some time t, where that time t is a security parameter. The longer you wait, the more time, the more secure, let's say, the protocol is. Because during that time t, somebody can just come in and say, no, you tried to cheat. Here's some proof that conflicts with this fact, which would happen in a very simple case that I have a payment, I made the payment, I paid Jack, and now Jack has my money, and then I try to also withdraw my funds. And that can be a problem. That's like a double spend. So you want people to be able to prove that fraud happened. So on the topic of the presentation, so Plasma, the thing in our veins, it's a chain. It's like a side chain, but it has a primary difference. You take the parent chain, so instead of having the starting and the destination chain, you have the parent chain and the child chain, or whatever term you prefer. And what happens is that you have an untrusted database manager, which usually gets called the operator, which takes all the content of the Plasma sidechain, the Plasma chain. It creates the Merkle root, so the Merkle root is the hash of all the contents in the block arranged in a specific structure. And then that root gets committed, it gets stored in a smart contract on Ethereum. And basically what you achieve is that you publish only 32 bytes of data on Ethereum, but those 32 bytes, they give you enough information combined with the game that I described earlier to be sure about the security of these transactions. So the characteristics of the Plasma chain is basically that you have a chain that commits, it is centralized, which people say it's a taboo word, but it's okay in this case, as long as it is non-custodial. Non-custodial meaning that there is no way for somebody to steal your funds. The finality of the Plasma chain is equal to the parent chain finality. So finality here means that as quick as each block gets committed, that's your confirmation time. So if I make a transaction, I still need to wait like 15 seconds or whatever. But what I can do is that I can make 1 million transactions and put them all in one block. And that's very powerful. And yeah, like the no routing requirements is because if you're familiar with payment channel networks or such as Lightning Network, if there are many nodes and you need to make a payment from A to B, like you need to go to find the path through all these nodes, and that's a very hard computer science problem. So Plasma is, what I say, non-custodial because you have the security from the parent chain consensus, and you have this exit game, where the exit game is what I showed earlier. And the desired properties of a Plasma chain is to be able to do micropayments. You want to be able to run the software on your mobile phone, so while having full node security. So currently, a Bitcoin full node is like 200 gigabytes. An Ethereum node is a bit bigger. Like, if you want to have full security, you must run a full node. But you cannot do that on a cell phone. No way. So what happens usually with your cell phones, if you use crypto, big question, is that basically you connect to a light client, to Infura, like to something else, and they allow you to make transactions. And that works, but it's not secure. And the final desired property of the Plasma is like basically maintaining security while data is unavailable, which the data availability problem is a very interesting topic, but it's a bit out of scope. But I suggest that you try to find the fake Plasma variants in this slide. Like, it's not trivial to do. So what happened was that in 2017, Vitalik and Joseph published the Plasma paper, and they started the madness of like Plasma XYZ with all the naming. And it extends a bit more like to a bunch of different ideas. It turns out, again, I will claim, this is just my opinion, that only one Plasma variant works from my perspective, because the other variants, what they have is firstly that they cannot do light client validation. So imagine that you have a chain which does 1 million transactions per second. Who processes these transactions if not a light node? If you must have a full node to process these transactions, you will need to store like terabytes or gigabytes of data on your phone. And like most people's phones maybe go to 32 gigabytes, like mine doesn't. And mass exits is a vulnerability which is present in the Plasma MVP or more viable Plasma that some companies are building on. And it's basically like a congestion thing where if something happens in the sidechain, you all need to rush and leave. But the thing is that it's like traffic jam. Like there's so much capacity on the parent chain, and there's many more people trying to exit. And eventually this leads to loss of funds. And so like this is my preferred variant, but let's take a moment to consider this very sensational article from CoinDesk which was that Plasma stalls, Snark starts to the rescue. Is that the case? So what I described earlier, I described that, OK, you have the Plasma operator which commits each block, and each block that gets committed, then you can use a challenge to cancel if fraud happens. So this is what we call Plasma with fraud proofs. Fraud proofs is the challenge, basically. But what you can do is that instead of having fraud proofs, you can have validity proofs. And what is a validity proof? It is pretty much that instead of having state, new state, and you assume that the new state is valid, what you do is state, new state, plus magic, basically, which allows you to basically prove in a very, very, very succinct way that the state transition from state 1 to state 2 was successful. How? Future reading for the audience. And what happens is usually that they either are fast, and you can do them great, but they have a trusted setup, which currently is being mitigated by techniques such as the Sonic construction, which is being worked on by Sean Bowe from Zcash. And alternatively, you can use a Stark, which is another zero-knowledge proof, but it's slightly bigger. Although I'm not an expert, so you can pick which is your preference. And just to take like a small history lesson here, channels have existed since the Bitcoin white paper. Like there is some reference where you can do, there is an insecure scheme on how you can do channels. The Lightning paper got released in 2015, and it was 6 years of iterations on designs, broken designs, better designs, until they got a design that worked well enough. And from 2015 until, I believe, March 2018 was only when the Lightning Network, Lightning Labs node went online to mainnet, beta. And still people are trying to get it to work. Comparing this to the Plasma, so we have August 17 Plasma.io, and you will see that like very, very quickly, there has been many iterations. And the claim is that basically currently, which is about the March, if you have been following Plasma Group's generalized Plasma architecture, like it's getting to the point where the protocol is more or less finalized. And it's all engineering then. And when people say that it's an engineering problem, it's basically a solved problem, maybe. So the claim basically is that we're in a much better state than channels, and I think that Plasma is like a very, very good solution that will solve the problem of scalability. And like the final takeaway that I want to take from this is that layer 1 is very complementary to layer 2. So if sharding works, it doesn't mean that layer 2 won't survive. Layer 2 is always needed, because even if you get to, I don't know, 1 billion users, what will you do for the next billion, and so on. And these systems, they allow you to go from global verification, where you have all nodes verifying the whole system, to some nodes selectively verifying parts of the system. Plasma cash flow is the real Plasma. Heard it here. The desideratum is that layer 2 security is always equal to layer 1. So it should be very, very clearly communicated that if there is some case where your security model changes, you're no longer in layer 2 domain. And there's a very, very good question, which I'm not able to answer, and I'm just trying to motivate here. If we can design a sidechain with fraud proofs that is better than a sidechain with validity proofs. Because validity proofs, they seem to be the best option. Like you always know that the latest valid state is correct, but they're more expensive. So can we design a system that with periodic, let's say, watchtowers, you can have them instead, you can have a better design than something where every state transition gets verified. And yeah, like if you're an investor, put your money in it because nothing gets done without that. And if you're an engineer, the material is, all the learning material is out there, so get involved. And happy to take any question, technical or not. And we have 5 minutes. Pardon? Yeah, so the problem in Plasma Cash was that when you deposit your coins, you get one leaf in the Merkle tree. Each leaf is a non-fungible token. So I have a 5 Ether coin, a 3 Ether coin, a 2 Ether coin. But I cannot have a 2.5. If I have a 5 one, I cannot split it. And what the interval tree does is that instead of having 5 Ether, 3 Ether, 2 Ether, you have 1,000 of 0.005 Ether. So you go from one coin to change, basically. And what the interval trees allow you to basically prove an inclusion or exclusion of a range. So I can prove basically the inclusion of a subtree of the whole structure in one proof, instead of having to provide 1 to 1,000 branches. So that's the main benefit. And there's a great interview with Ben Jones and Alex Kidanov where they talk about it in extreme depth. It's like an hour video on YouTube.